Hey, welcome to chapter 2, which is going to be kind of getting into the nuts and bolts of what calculus is really about. We spent the first couple of weeks really building an intuitive understanding of the two main concepts of calculus, which are slope of your tangent line, and that's what we're going to focus at here in this chapter, and dealing with area underneath the curve, which we'll start focusing on once we get to chapter 4. And then we introduced the idea of limits in the last chapter. So your tangent line problem that finding the slope of your tangent line, the relation between distance, velocity, and acceleration we looked at, and we've looked at a little bit of finding max and min, and the first couple of weeks we looked at finding area. So we're getting into the more of the nuts and bolts when you get into the tangent line problem. Essentially, if you have 2 points that are h units apart, like we looked at before with the IROC formula and the average rate of change formula, um, you can also go ahead and here they're saying you have a point C and f of C, and then C plus delta x and f of C plus delta x, where basically you have this point at C and another point that's delta x over, you get this. It's really the same as your average rate of change, just different variables on the inside. And then this is really the same as your IROC, just using different variables inside the parentheses. But essentially it's the same thing. So that's what they're getting at here, is trying to lead up to that. So same thing you've seen before, same thing that's in your vocab, just with different notation of what's inside. So here, if you're looking for the slope of your tangent line, well, we know we always need to have a point and we need to have a slope. So to find your slope, you have to do your IROC formula. If you don't want to do this, use your IROC formula that you've used before from your vocab. Um, it's going to accomplish the exact same thing, would not make a difference. So pretty much all you have to do is go ahead and plug in um, c plus delta x, or x plus delta, or x plus h minus f of x all over h. Um, Going back to your normal IROC formula, that's what I used here. It's going to accomplish the same thing. It takes something more familiar to what you have. Then you'd have to take x plus h times x plus h, FOIL that out, distribute through your negative 3. You would then get this here. Distribute through your negative, you get this here. Now you can go ahead and collect your like terms. You'll notice your 2 and your minus 2 will cancel. Your minus 3x squared and your plus 3x squared will cancel, leaving you with this. Then you can take an h out of everything, top and bottom, and you would get this here. And then you can cross those h's out, special form of 1. Now at this point, since you got the h out of the bottom, you can actually plug in your limit as h approaches 0, so plug in 0 for h. There's no h's here on the negative 6, and then you plug in 0 for h. Well, then you just get negative 6. Remember, your derivative, your IROC, is your slope predictor function. So for our given problem up here, what we have right here of negative 6x tells us our slope anywhere along this function. And we want to know our slope when x is negative 1. So let's take negative 1, plug it in for negative 6, and then we can finish solving it. So now we have our slope, and we have our point that we were given. Well, then all you have to do is just use your point slope formula, y minus the y value of your point, equaling your slope times x minus the x value of your point. Distribute through, get y by itself. So that's really all we're doing here. For the most part, it's a review of what you've already done before. So here we're starting the idea of looking at your differential calculus or differentiation, which means you're really deriving something from your original function. And so that's what a derivative is you're deriving something from your original function. So whether you are looking at this or your normal limit is h approaches 0 of f of x plus h minus f of x all over h, or using this idea right here with t and delta t, really it's the same thing. So asked to find the derivative of this, you go and take your function, plug in t plus delta t right here. That's what we would get here, minus your original function all over delta t. FOIL this out, t plus delta t times t plus delta t, distribute through your 4, distribute through your negative through the second set of parentheses, all over delta x. Then you have some terms that are going to cancel out. Your 4t squared here is negative, it's positive here. Your 5 and your negative 5 cancel. Then you can go ahead and pull out a delta t on the top. You have delta t times the top, delta t in the bottom, the delta t's drop. Now that you get that delta t out of the bottom, you can plug in your limit as delta t goes to 0, so you plug in your 0 right here. That disappears, then giving us with 8t. Personally, I don't like to eat my tea. I like to drink my tea when I have it in the morning, but we get 8t. Yes, that's a dumb pun. So that would be our derivative. Our variable was t, so that's why we ended up with t here. Now, a side note, but very important thing, is your derivative is typically written as f prime of x. Occasionally it's written as y prime. It's also quite common to see dy over dx. These last two here are less common, but any of these notations right here are your derivative notation. So make sure you're familiar that whenever you see any of these, that you know that it just means find your derivative. Remember these. Hint, hint. So here, find your derivative. Well, all we have to do is your limit as h approaches 0 of f of x plus h. So plug in x plus h here, and that gives us this here. Minus your original function gives us this here, all over h. So to work this out, all we'd have to do is write the top as one fraction. So we'd have to do a common denominator. So we'd have to multiply the first fraction top and bottom by in root x plus 1. Second fraction would need a root x plus h plus 1, top and bottom, both special forms of 1. Now we can write the top as a one big fraction of this root minus this root all over our common denominator. And you might be wondering, well, where did this dividing by h go? This is really dividing by h over 1. So I multiplied by the reciprocal, which puts the h on the bottom. Now we still have to keep working to get this h out of the bottom before we can really take our limit, because in any of these steps here, if we went ahead to try to plug in h being 0, we get an indeterminate form of 0 over 0. So to get the h out of the bottom, because we're dealing with roots here, we're going to do the conjugate of the top and the bottom, or do the conjugate of the top and the bottom. Remember, conjugate, you switch your sign in between from a minus sign to a plus sign. Then you'd have to FOIL the top, root x plus 1 times root x plus 1. Remember, when you're multiplying conjugates, your outer terms and your inner terms cancel, because one of them ends up being positive, the other ends up being negative, but they're identical. Then you'd have to do your last terms. Notice it's a negative root times a positive root, so we get a negative. Same root times itself, so the root cancels. Still all over that denominator. Notice I didn't go ahead and multiply it all out, because that would be really annoying. It's going to be simpler if you leave the bottom in parentheses. Looking at the top, you could distribute through your negative. Then you could go ahead and collect like terms. You'll notice the only thing you're left with on top, because your x's drop, your 1's drop, is just a negative h. You'd have a negative h on top, which would cancel out with that h on the bottom. So that's why we just get a negative 1 on top. That h is gone on the bottom. Now that we got that h out of the bottom, you could plug in h being 0, plug it in here, and plug it in here. Well, when we do that, plug in h being 0 here, we get a root x plus 1. We get another root x plus 1. Then plug in h being 0 here. In parentheses, we get a root x plus 1 plus another root x plus 1. So what we have here in front would really just give us an x plus 1. Here, this would give us 2 of those roots. So we would get this. Now, if you wanted to write the bottom as an x plus 1 to the 3 halves, because remember the root is a 1/2 power, this is the first power, you could. Would not make a difference. But that would be your derivative. So let's talk a little bit about our derivative as it's related to your original function. Over here, we have our function of this graphed, and that's in blue. That's this blue curve comes along, all of a sudden goes straight up, and then starts to curve off to the right again. If you graph your derivative, because remember this is a 1/3 exponent, you'd put the exponent in front, decrease it by 1. Um, so needless to say, I'm missing a 1/3 here, so we'll put that in. So it would cause a 3 to be on the bottom. We would get this. That's over here in red. Now notice, if you looked at the slope of your tangent lines anywhere along here, you're going up, so it'd be a small positive, but here it's a steeper positive, so it's going to get to be a bigger positive. But you notice as we come along here right at 0, or the origin, 0, 0, it ends up being a vertical tangent. So that's why as you get really close to 0 from the left-hand side right here, it goes up to be a very big positive number. Now notice, over here, just to the right of 0, it ends up being still a big positive slope here. So just to the right of 0, it's still a big positive value for your derivative. If we continue along here, you'll notice our tangent line would be more about like this. So it's still a positive slope, but not as big a value. As we continue along here, our tangent line would still be positive because we're going up, but the slope would be a much smaller positive value. So that's why we have this down here of being a smaller one. But the main thing here is that our original function is continuous. But our derivative is not, because right here we have a vertical asymptote because we had a vertical tangent right here. So our original function was continuous, but our derivative was not continuous. So keep that in mind. Here's another example. We have this particular problem. If you graph its derivative, you'd have to be concerned about that, because what we have here coming into x being 0 from the left, you would come in here and you get a bigger and bigger, steeper and steeper positive slope. So from the left, coming in here to 0, the slope of your tangent lines, which is your derivative, ends up being a really, really big positive number. However, once you get to the right of 0, oops, sorry, just a second, grabbed the wrong thing. Just to the right of 0 here, come on, there we go. It would be tangent lines like this here, which would be a negative slope because we're going down, but it would be a big value. So just to the right of 0, your derivative is a big negative number. So here you'd have a positive slope because you're going up, and it will get to be a very big positive number on the left. But just to the right of 0, you'd start at a big negative number, and then as you continued along here, these are all negative slope tangents here. So your derivative would not be continuous. So once again, here we had a continuous function, but your derivative was not continuous. So if your function is differentiable, meaning you could take the derivative, then it means your function is continuous. So if you can take your derivative and your derivative exists, that means your function is continuous at that point. So differentiability implies continuity. So if your derivative exists at a certain value, then it has to be continuous at that point. But the reverse is not true. Some people think that if it's continuous, then your derivative will exist. And we just saw two examples where it was a continuous function, but your derivative did not exist at certain spots. So continuity does not imply differentiability.